Hi, welcome back to this video on static indeterminacy of frames. This is the figure that we have seen in our last video. Okay, so we are going to solve this problem using the formula as well as the open tree method. Directly, let us start the problem. We can see that m equal to 16, r equal to 9, and j equal to 14 in this case. So if we directly use the formula to determine the overall static indeterminacy, the formula is 3m plus or minus 3j. It gives a value of 15. Okay, we can now classify this as external and internal. External, for determine the external static indeterminacy, we have the formula r minus 3. So r is equal to 9 here, r minus 3 will give a value of 6 here. Okay. And then internal static indeterminacy is given by s minus se. So this 15 minus 6 gives a value of 9. What does that mean? There are 6 external, I can say 6 reactive components that are in excess, which can't be determined using the equations of static equilibrium. And similarly, we have 9 surplus internal stress resultants that can't be determined as such using equations of static equilibrium. Okay. So now let us try to solve the same problem using the method of open tree. So in order to do that, we need to choose a fixed support. Okay, if it already exists, otherwise we need to induce one. So we fortunately have one here. So this is the fixed support which this resulting tree will stand by. Okay. Second step is remove all other reactive components. Okay, so we have two reactive components here, two reactive components here, and two reactive components here due to the presence of two pin supports at location A and G and a guided roll support and N respectively. So 2 plus 2 plus 2, sum of that will give you what is the external static indeterminacy. Okay. The final step is to cut open all the loops. You can do it in different ways, but what I am doing here is I am cutting across this member, and this member, which is first member is connecting joint CAG, second member is connecting joint BF, and third member is connecting joint I and L. Okay, whenever we cut across any member in a frame, there are three internal stress resistance being released. So 3 here, 3 here, 3 here, sum of that will give a value of 9. Okay, so that is the internal static indeterminacy. Now when we sum up this, that will give you the total static indeterminacy. You can check that the same values are obtained. SC equal to 6, a formula, and this open tree method, and SI equal to 9 in both methods. Fine. The wonderful tree we produced even without having any seed is here. You can see that this stand on its own leg. Okay, and then we have the arms, all of its arms open. Okay, so this is fine. Let's move on to the next problem. Here we're going to do the same here, but something extra is seen here, which is the presence of internal hinge here, here, and here. So if we remember what we did in case of beam, if we have a beam without any internal hinge in it, okay, just this is a cut section from a whole beam, and in this case, if we don't have an internal hinge, if I want to establish equilibrium at a particular point, we can say sigma mz equal to 0 at that location, but we can use this equation only once. Okay. However, if at the same location and an internal hinge is introduced, we said that the bending moment will be released here. Okay, so that's what I have indicated here. Only I am representing the shear force, but bending moment is 0. That's why I didn't give this pair. So what does that give is, it gives a condition that we can use sigma m equal to 0 for this separately and for this part of the beam separately. So if we don't have the internal hinge, we get only one equation sigma equal to 0 once. However, if there is an internal hinge, we get two of that conditions. Okay, so the idea here is, if at a joint we have n number of members, then the number of equations of condition we get is n minus 1, because without that particular internal hinge at that location, only once we can write sigma m equal to 0. For example, I can take this particular joint. Here we have 4 members being connected. If this internal is not available at this location, only once I can use sigma mz equal to 0. But if it is present, the bending moment is released at all this location. Okay, so I can use sigma m equal to 0 for each of this member. That means 4 times I can use. If it is not there, it is just one time. But if it is there, the equations available is 4. So how much we get in excess is 4 minus 1 equal to 3. So similarly here, 2 members I have 2 minus 1 equal to 1. Here I have 3 members connected at this joint, so 3 minus 1 equal to 2. So 1 plus 2 plus 3. That's what we need to account for here. Okay. So if we start with the formula directly, 3m plus or minus 3j, that gives you the static indeterminacy in case internal limits are absent, but we do have them, so we need to account for that. As I said earlier, the extra, or I can say the equations of condition available at joint E is 1, at joint I is 2, I mean the number of equations of condition, and finally at joint G is 3. So 1, 2, 3. Sum it up, it gives a value of 8. And particularly, you can see that in this case, I am not categorizing the static indeterminacy as internal and external, because in case of frames, depending on a problem, you can regard it as internal and external. Okay. But there are problems that you can clearly tell this is internal external. It may be a little confusing now. Maybe in the another example to follow, it will be made clear. Okay. And then again, you can use a method of open tree. Fine. I'm not going to explain in detail because in the first problem we did that already. Go by the same way, just that I'm showing these three numbers. Sum of that will give a value of 5, and then these three numbers corresponding to interest resultants resulting in 9, and then this 6 is for the presence of intelligence. So you can see that these two numbers are on the same. Okay, the resulting uh, open tree is this. Okay, you can see that all its sums are open. Fine. Let's move on to the next problem. In this one, we'll establish that whether we call the static indeterminacy internal or external is one's own choice. Why do I say so? Because in this problem, if we approach this problem by the way how we usually solve, SC is given by what? R minus 3. Here we have 6 reactive components, so 6 minus 3 equal to 3. Right? That means there are 6 excessive reactive components which can't be determined using equation of static equilibrium. Either one can choose the triad to be here or here, and just considering that the unknowns are present here. If that is the approach, we can say that this indeterminacy is external, but that is not the only way in which this problem can be solved. The other way is you can cut across this number. When you do so, what happens? You get two beautiful trees this time, not a single tree. Okay. So whenever all the supports are fixed ones, this is quite helpful because you can cut across the spans of the beam and produce several individual trees which are each statically determined. When we carry out that operation, wherever we cut, we are exposing three internal stress resistance. For example, here when we cut across this member BC, we expose this or release this axial force, shear force, and bending moment. If we solve the problem with considering this as unknowns, then one can see that the indeterminacy is internal. Okay, hope this makes sense. Just that you need to stick to what your tutor expects from you, or if you're writing a competitive exam, you need to be clear based on the previous year question papers that what the uh, person who sets the paper expects from you. Okay, but just I'm giving a general idea of how it can be. Okay, finally, we'll have a look at this particular problem. Here we can see that we have just two rollers at these locations D and E. So directly R equal to 2. So 2 SC is equal to what? SC is equal to R minus 3, which will be negative. That means what I can say is this particular frame is unstable. Okay, and there is no other point in discussing this further because if it is unstable, we are not going to use it. Okay, but in case if you want to find what is the static indeterminacy, you can do that 3m plus or minus 3j minus 1. This minus 1 is due to the presence of internal at this location B. It will give you a value of 1. The same can be done using the method of open tree. Okay, but the only difference here is we have both of them as rollers. So we need to create one virtual fixed support somewhere. I'm considering here. In a fixed support, we have two translational restraints and one rotational restraint, right? But in a roller, we have only one translational restraint. So we need to induce two more of them. That's why I have minus 2. So including this minus 2 means that I'm going to consider this as a fixed support with which this tree will stand. And second step is release all other reactive components. I'm releasing the reactive component here. So plus 1. And the last step is cut open any loop if exists. So this loop I'm cutting across this number and releasing the interest resultants, due to which I get 3 here. Okay. And finally, we have an internal here. So we need to add them up. 3 minus 1 plus 1 minus 2. That also gives a value of 1. Just that I'm saying the formula and the method of open tree is useful depending on the context. But there are problems where the open tree method will be quite helpful. Maybe in the subsequent video, we'll come up with a problem where we can establish that it is very handy. All right. That's all as of now. Thank you so much for your patient listening. We will meet again in the next video where we will see some more examples, particularly on instability of frames. All right. Thank you so much.